Welcome back. We're going to have a moment here to talk a little bit about some maintenance practices, a few more bits about generator regulation, and a few best practices with wiring and circuit protection. So let's get started. First, let's take a look at our two main circuits for a DC generator that is using a shunt winding. So we have three types. Remember, we have a series generator, which is not commonly used, but is much more often used as a DC starter motor because of the high initial starting torque, which, again, just as a refresher on that, as the motor starts, we're going to have a very high inrush of current, which is going to get the motor spinning. However, that current is going to decrease over time because as the motor spins, it's going to have more EMF resistance built up between the armature and the coils. It's going to kind of try to act like a generator because it's rotating now, so we're going to get a little pushback, which means the current that moves through the motor is going to decrease a little bit. On the flip side, when we talk about generators, that quality that we would see in a series winding is not particularly helpful for regulating generator output. We're trying to maintain a constant voltage, so anything in the system can operate at that voltage. It's also how it's going to charge the battery by remaining at a constant voltage, but adjusting the amperage or the current flow to meet the needs of the load on the aircraft. So as we look at this is a shunt wound generator. This is the most common type we'll see with low to medium output generators. We may see a compound winding with higher output generators, but we don't really see those too often anymore, especially since most aircraft that have major requirements for electricity are going to be done with alternators. So let's take a look at just these two options. Now, one thing to remember is a generator is not so much a creator of electrons as much as a electron pump. So if you think of this more of like a fuel pump than something that just creates electrons out of thin air, then it makes a little bit more sense. Up at the top here, we have our positive terminal for the armature, and that is connecting to our positive insulated brush that attaches to the commutator on our armature. Now, branching off in parallel from that is our shunt field that crosses through here, which is going to go to the field terminal on our voltage regulator. Remember, the whole point of voltage and current regulation is that we are changing the field current. We aren't doing anything really to the armature, we're just changing the field current. As a result, on the other side, our grounded brush, where electron flow is going to exit, will go through the other side of our armature, and that is where it's going to head off to the armature in position on the generator control unit or voltage regulator before it heads out to the battery. So that's what we're looking at. The B circuit operates fundamentally the same. It's still in parallel. So we have a parallel path which diverges up here for our input to the armature. So we have the armature flowing right here. We have that current flowing through the voltage regulator through the field, through that field, and then we meet up at the common ground. So it's still in parallel. It's just a different way of wiring. It can seem a little confusing at first, but it's really not too bad. And again, it's mostly something that you need to factor in if we're, say, testing a generator or flashing the field to make sure that we hook up to the right terminals on the generator to be able to pass current through in its normal direction of flow. Now, as we take a look at the 3-unit generator control here, I just want to clear up a couple things because these can be a little bit confusing. So I'm going to use a couple different highlighter colors here. Now, first off, this area that we're looking at right here, I'm going to draw a highlight right here. It's not a very straight line. This is our field circuit through the generator control. So what that means is that we are going to be passing field current, right? Remember, we branch off wherever we do in an A circuit or B circuit. In this case, we're looking at an A circuit generator. So we branch off from the field and we move up and have to pass through our current limiter contacts and our voltage regulator contacts. Now, the two pieces right here, our current limiter coil and our voltage regulator coil, both of these are coming off of our generator output. So this is actually sensing what's coming out of the armature and would be going to the electrical system load. So we'll highlight that in a different color to make it a little more obvious. Here is our generator portion, and I'm just going to draw a big circle around this section to show what is connected to our generator output side. So you'll notice as current flows out of the armature, it's going to come up through this generator port and we will energize these coils. If we have too much current or too much voltage, it's going to separate these contacts and it's going to break the field coil. Now, because we have a fair amount of current that's moving through the field, if we just break those contacts indiscriminately, then we're going to have issues with arcing. And mostly due to the fact that we've built up residual voltage, we've built up active voltage due to the current flow, and now we have to dissipate that somehow. And that's where these resistors right here come into play. The whole point of those two resistors is to help dissipate the stored voltage or the built up voltage when those contacts break apart. That's going to help reduce the amount of arcing we see between the contacts on our voltage regulator and current regulator. Now, if everything is working normally, our field stays closed, so these contacts, they remain normally closed, so we have current flowing through the field, which is allowing us to output more voltage from the generator. Once we reach the nominal battery voltage of the system, this coil right here, again, which is being wound by our generator output, is going to close the contacts that we have right here. If we do not have enough current to do that, we don't have enough force to close these contacts, so we are actually electrically separated from the load, from the battery. And what that's doing is it's preventing current flowing backwards through here, energizing the armature and turning it into a motor. That's ultimately what we're trying to avoid. So just a little bit of clarification on those couple points. Now, as we move on, an average installation, we're looking at a couple DC alternators right here, but we need to talk a little bit about switching and circuit protection. Now, obviously, the current that's coming off of our generators, right, that's being output, that's going to the system bus, is pretty high. As a result, it isn't going to work for us to put a switch on that current. The other situations where we'd have that much current flowing through would maybe be like a starter motor, in which case, rather than using a switch in the cockpit and running that voltage through the cockpit, we would use a solenoid. So we could use a solenoid effectively as a remote switch to be able to actuate the starter. And again, when we talk about that kind of thing, a starter is not something that would require a circuit breaker on it because of that high inrush current. It's not going to work. We aren't going to have a circuit breaker on that circuit. But when we talk about generators, it's a different thing. So in this case, we're looking at two DC alternators, and we have two circuits. Remember, we can control the generator or the alternator by manipulating the field circuit. With an alternator, remember we are using direct current of varying current flow and voltage to change how much we are producing through the stationary armature on those alternators. So if we want to switch off the generator, if we put a switch that is manually controlled in the cockpit on the field circuit to both those generators, then we can effectively turn the generator off. And remember, an alternator, it's not like a DC generator where we have residual voltages produced either. If we turn off the field, it just turns off. That's it. Now, on these two switches, we have circuit breakers that are installed because we are still running current through the field, but the field current is significantly lower than what the alternator itself is outputting. So that's why we see a couple of 5 amp circuit breakers on the field circuit, but we see 100 amp circuit breakers on the output circuit. So we have 2 layers of protection. If the alternator overvolts, if we have a failure with the voltage regulator or something like that, then the circuit breaker will blow. Conversely, if we have an issue with the field coil where we overcurrent, then we can blow the circuit there and we can maintain a safe condition in the aircraft. Having these 2 switches is actually a requirement of design. So when we talk about design requirements, we're talking way back early on in the CFRs. So like Part 23, that general region, depending on the aircraft type certification, those are where those requirements come from. So we have to have a way, if we have 2 generators running, to be able to switch them off independently so that if one malfunctions, we can separate that from the electrical system and continue using the other generator. Just a little side note on something that can happen here. So when we look at this 3-unit control, we have contact points, and they're mechanical contact points. They're basically relays, and relays are prone to have mechanical failure. Not very often, but it is something that happens. So, in an odd situation, if, for instance, these contacts that are normally open fuse in a closed position, then we could potentially have reverse current come through the battery uncontrolled, or come through the generator uncontrolled, and would cause it to try to motor. We may not notice when the engine is running and it's producing current at that rate, but when the engine stopped, we may see a significant draw on amperage if everything else is shut off. So if we saw a draw on our amp meter and everything else in the aircraft is turned off, it could be because that reverse current relay has fused closed. Now, on the other hand, with our current limiter contacts and our voltage regulator contacts, if either of those fuse closed, then we could see uncontrolled output with the generator. So if those are not able to break and regulate the field coil, then we're going to have a lot more current flowing through, and it produces some problems for us. Now, as we talk about problems with generators, we have a few different things that we need to verify to be able to make sure that it's operating correctly, especially when we have a generator pulled apart. So in this case, we're looking at a commutator, and we have an ohm meter that's hooked up to check for any shorts between the commutator and the armature shaft. Now, this would be a problem because we need that generator output to go through its carbon brush to go through the regulator to be output into the system. However, if we do not have that happen, if there was a short on one of these mica layers where we have current flowing through the shaft, then it would ground out to the casing and we wouldn't get the output that we're supposed to have. So we can just do a simple ohm meter check on each one of those commutator sections to the shaft to see if we have a shorted out ground. Now, on the other hand, if we're looking for an open armature coil, meaning that there's a lack of continuity, we actually have to run some voltage through to see. Now, as you've seen in lab, if you have a growler that's so equipped, it will have a double set of prongs that we can use to run current through these commutator sections to check for open armature coils. A couple things can happen. If we have a open armature coil, then we may not get the correct output from the generator. If we had a shorted armature coil, which is something that we check with the growler and a metallic blade, something that's ferrous so it will react to the magnetism, what we could happen to have is that we over current or over amp that, and we could actually melt the solder that connects that winding to the commutator right there. And a good way to be able to check that even before we got it out of the generator is if you have issues getting output from the generator and we've already flashed the field and we know everything's fine, the brushes appear to be okay, but if you aren't getting any output and you take a look inside the generator and there's a lot of solder that's thrown around on the end plate that would be around this section of it, chances are that's probably solder that came from one of these commutators as the solder let go as the winding overheated and we have a short. So that's something you may see if you're troubleshooting. Again, this is a demonstration, so for checking for a shorted armature coil, we have a transformer in the growler here, which is going to produce a magnetic field. If we do have a short through, it's going to make this blade start to vibrate violently against the other end of that winding, and we would see that on both sides as we run that magnetic field through. Now, additionally, if we aren't talking about armature problems and we're talking about field problems, when we check the field on a generator, we need to make sure that the armature is removed because the armature is going to provide that electrical continuity between it, the side that we're testing, and ground. So there's a couple checks that we would do with the field. We would check for a short to ground on our field coil. So if we were shorted to ground, effectively that would cut the voltage regulator out of the system because we would be regulating the field coil, in which case that field is going to produce as much current as it wants, which in turn is going to drive the voltage way up on the armature output. So if we had a complete failure in that way, that's where probably our circuit breaker would come in and prevent any damage to the wiring, which we'll talk a little bit more about later. But when we do talk about circuit breakers, keep in mind that circuit protective devices, switches, it's all going to be based upon the wiring that's going between the circuit protective device and the actual item itself. It's not so much about protecting, say, an alternator or a generator from blowing itself up. What we really don't want to have happen is have the wiring over temp and start a fire. That would be the biggest thing that would cause an issue. And so the circuit breaker is going to protect us against that, which is why our circuit breaker should be set to below, basically below the threshold of what would cause the wiring to over temperature and have a problem. All right, another method we have here is checking for continuity through the field coil. So we can check for an open in the field coil by putting a multimeter lead on the armature terminal and one on the field terminal. And basically all we're checking for is to make sure that this entire winding down to the brush and through the field poles is all intact and we don't have any opens in it. So again, this would be a continuity check that we do with an ohm meter. As we talk about brushes on generators, since they are carbon, they will wear out over time. And so as a general rule of thumb, this isn't a hard and fast rule for every generator, but as a general rule, once we reach 50% of the original length of one of those carbon brushes, it's time for them to be replaced. Additionally, you can see here being demonstrated some sandpaper. This is going to be very, very fine sandpaper of a non-oxide variety. If we have oxide sandpapers or a metallic grit sandpaper, then it's going to cause issues where we start getting arcing and we can potentially end up creating a short on the commutator because that oxide can get stuffed into the micas between the commutator sections, and then we end up with shorts throughout the commutator, so we really don't want that. So make sure we're using a non-conductive material for the sandpaper that we do this. But basically we're just going to run the sandpaper right underneath the brush, and we can move that back and forth underneath the brush to get to take the shape of the commutator. Once that's done, we can remove the sandpaper and do just a little run-in. So motor the generator through for a little bit with no voltage on it to get those carbon brushes to seat properly. All right, flashing the field. We talked about this before. It's important to know if you have an A circuit generator or a B circuit generator. And like I mentioned, this is probably one of the most important aspects of knowing the difference between the two, is mostly just where we're going to put the source of electrical power when we do that. So remember, with our A series, we make a connection up here at the carbon brush on the positive side of the armature. So as a result, if we take a look where our path is going through, our field terminal is going to be ultimately the ground path for the field coil. So that means if we hook up a power supply to flash the field, the normal direction of current flow means we'll hook up a positive lead to the armature and a negative lead to the field terminal, and we can pass current through to flash the field to restore the magnetism in those poles. On the flip side, if we have a B circuit generator, remember here that we are actually taking current from a different place. It may not be off of the circuit inside the generator. What we've done is we have a parallel circuit that starts somewhere outside of the generator. So that's where we're pulling power in to the fields. That means it just switches a little bit. Since we're sharing a common ground on the commutator, then we are going to ground a negative terminal to the ground of the generator, and we're going to attach our positive terminal to the field terminal. That's how we would be able to flash the field on a B circuit generator. So that's really the whole point of knowing the difference between the two. Moving on to DC alternators. So when we check, it's going to be a similar procedure for what we see with DC generators. We want to make sure that there's no openings or shorts with the windings in our field. Since our field rotates in a DC generator, we have two slip rings. We can do a continuity check between the two slip rings to check for shorted windings. We can do a check between each slip ring and the rotor shaft to determine if there's any grounded windings. Similarly, when we take a look at the armature, so the stationary portion of the alternator, we can check for grounds by going to the pole casing around the windings and to each one of these different phases. With a three-phase alternator, we are sharing a neutral, which means to check the field coils for, or not the field coils, sorry, the armature coils here, the stator coils for continuity, we can check our resistance from phase to phase to be able to see how that works, because we share a common neutral. So that's how we can manage that. Additionally, we have diodes that are installed in DC alternators to rectify the electron flow and to prevent reverse current from coming back into the alternator from the battery. So as a result, we can use, most multimeters will have a diode checker, and so each one is made a little bit differently, but effectively we're going to have a housing and the input lead, and we're going to touch our rectifier checker to that in either place. What we should get is one direction where there's high resistance, where it's going to be resistant to flow, and another where we have low resistance. Or if we have a diode checker, then we'll see an indication on that when we're in our diode mode in one direction, and the other will get an open line indicating that we don't have continuity. So it just depends on what style. For each one, you're going to see two diodes because we're preventing reverse current from the battery, but we're also making sure that current exits the alternator in one direction. So you'll actually have 6 diodes, 2 for each phase of that DC alternator. So just something to watch out for. All right, moving on to a little bit about wiring. So as we look at wiring, we need to think about a couple different factors here. Whenever we're installing something new, whenever we make any changes, we may have to change wiring, or we may need to make sure that the existing wiring is going to be sufficient. So remember, when we take measurements on wires, we're going to use a wire gauge, and it's going to be measuring the conductor, not the insulator as well. We're just measuring the conductor inside. But hopefully this should be a little bit of review depending on the circuit voltage that we're operating in. In this case, 14 and 28 would be the most common with our DC systems. We're going to find the length of feet in the run that we want to do. So let's say we have a 10-foot run on a 14-volt system. So that means I can come to my 14-volt column all the way down to 10 feet, and I have a line that's going to project out for 10 feet. Now what I need to do is figure out the amp requirement and the condition that the wire is going to be in. So if I have wire that's in a conduit and a bundle, I'm going to take a look at curve 1. If I have a continuous flow of wire that's in free air, then I'm going to look at curve 2. And if I have an intermittent rating, so let's say something like a starter, for instance, then I would look at curve 3. In this case, we have 10 feet on 14 volts. Let's say it's a starter, so we're going to go with curve 3. And let's say, we have something crazy like 100 amps for our inrush current on that. So I'm going to follow our 100 amp line right here all the way down to curve number 3. That is our intermittent rating. As I see where this intersects, oh good, that's below my threshold, so I don't need to worry about not being able to use this. I apologize for a little technical difficulty there. So again, in this case, we don't need to worry about not being able to use this particular run. So we have 14 volts at 10 feet. I'm going to come across and see where it intersects my 100 amp line, which is right there, and I fall in between the 8 and 6. I'm going to go to the larger conductor, which means we would use a number 6 wire for that particular run. So that's how it works. Pretty straightforward. As we talk about wiring things in an engine bay, it's important to be cognizant of how we're wiring things. Now, this is an area where people can get pretty sloppy, where we just start stacking connectors on top of a terminal, especially if we're grounding things. And there are rules. According to the FAA, we cannot do more than 4 terminals to a single terminal lug. So one of these studs can only take up to 4 wires. If we have to do more than that, then we have to use a bus strap between the two to connect them. Additionally, when we strap these on, it shouldn't be just willy-nilly. We have to make sure that we angle these away from each other. You can see that the way our ring terminal here is connected, we have the flat portion, and then we have the higher portion where we've made the indentation for our crimp there. We want these to be angled away from each other on the same side to prevent contact between the two. We want to keep these separate and distinct. We don't want to have anything crazy going on. Additionally, when we look at these terminals, if we are installing new wire numbers, a lot of times we'll have wires that are already printed from the factory, but if we're putting something new in, as a general rule, we should not have to look any more than 3 inches away from a terminal or a terminating point, to be able to find what that wire label is. So if you're installing one, make sure it's within 3 inches of a terminal, and then as we carry on down the wire, it shouldn't be any more than 15 inches along the wire that we have those indications on the system, on the wire that is. All right, last couple things we'll talk about here with circuit protection. So when we use switches to control a system, we have switches that are going to be designed for a nominal voltage and current flow based upon a couple different factors, the housing of the switch, what it's designed to be able to accommodate. Now, there are some situations where we have circuits that may have a higher inrush current or may have a tendency to generate more heat at different points. And so as a result, we have to derate those switches. So derating factors just refer to a bit of math that we accomplish in order to figure out if we can use that particular switch on that circuit. Now, this shows a couple examples of derating factors. Something that's really important to take away from this is anytime we have not just a motor, but a DC motor specifically, those always have a much higher inrush current, and they always have to be derated when we use switches in line with a DC motor. So just get that one burned into your brain because it's very, very important. As we talk about circuit breakers and fuses, most commonly we're going to see circuit breakers used throughout the aircraft. And we're going to see a couple main varieties. We're going to have a push to reset type where it just pops out and then we can push the breaker back in. We have the push-pull type where you can manually trip the circuit and then push it back in. And then we have the toggle type, which looks a lot like a regular switch, but it's an actual circuit breaker and it will trip into the opposite position. A note on those as well, whether it's a switch or a toggle type circuit breaker, when it's installed on a panel, it should be installed in such a way where the up or forward motion is going to be on and the down or aft motion is going to be off. Again, just a little bit of review there. But again, these are some general requirements for the circuit breakers, basically their amp rating, to each kind of conductor. Now, this is not, again, a hard and fast rule. It's going to depend on what we're running on that circuit. And so we want to make sure that we use the right circuit breaker for the right application and is appropriately rated. Additionally, for aircraft, we are not allowed to use automatic reset types, and the circuit breakers that we use must be trip-free, which means if someone gets a really bright idea that if a circuit breaker fails, they can just push the breaker in and try to hold it to force the circuit to work, that's not going to work. Don't do that. It's a terrible idea. People really shouldn't do that. So we can't have those in airplanes. Unfortunately, we can't trust people to not try to do that, so we just don't allow them in airplanes. They must be trip-free as well. So just a couple notes on this. Like I said, this is a bit of a crash course, looking at a review in some cases from what you've probably learned in airframe, but focusing a little bit more as well on some of the maintenance pieces that we have with our armatures, generators, alternators, all that fun stuff. Hope it's helpful, and we'll see you next time.